Hello everyone, thanks for attending this tutorial from Qualcomm about advanced network quantization and compression through the AI Model Efficiency Toolkit. So we have two presenters today from Qualcomm. So first, let me quickly introduce myself. I'm Edith Beignet. I'm from Facebook, so I have the pleasure to moderate that meeting today. So we have two presenters who are going to alternate after around 25-30 minutes, I think. Feel free to ask all the questions on the Eventy platform. I will try to ask all the questions after the first part and maybe during all along the second part. So please be active on the Eventy. I'm going to check that all along the presentation here. So our first speaker is Chirag. Let me just open the bio because I won't be able to do that by heart. Yeah. So our first speaker is Chirag PATEL. He's currently a principal engineer and manager at Qualcomm in the R&D AI research team. And he is the project lead of the Model Efficiency Toolkit that you're going to see today. So I think we have the exact right presenters for that tutorial today. He is responsible for bringing the neural network model efficiency R&D to practice, working with interdisciplinary teams, feature roadmap planning, and customer engagements. He also leads projects for enriching smartphone user experience using combination of machine learning and low power, always on sensors and forward-looking technologies. So prior to this role, he has more than 10 years of experience in wireless communications as a research engineer, leading design and standardization as standalone LTE in spectrum, unlicensed spectrum and 3G, 4G small cell technologies. And finally, Chirag holds a PhD in EE from Georgia Institute of Technology. Thanks, Chirag. So I think it's your turn now. Please let me know if you want me to check the timing, but I think you already have that in mind when you leave the floor to your colleague.
Yeah, thank you, Edith, for the kind introduction. Welcome, everyone, to our talk on advanced network quantization and compression through AI Model Efficiency Toolkit. So I'm going to use AIMET in short for AI Model Efficiency Toolkit. So AIMET is a product of Qualcomm Innovation Center. It is basically a library of state-of-the-art network quantization and compression techniques. We are excited to talk more about it. Like we will show during the tutorial, highlight our model efficiency research and how we bring this research into practice to enable the AI community to gain the benefits through the AI through the AIMET toolkit here basically. So we all know, right? Like AI is today all pervasive. We see AI in IoT devices, in smart homes, smartphones, cars, robotics, drones. It's everywhere, right? With the increasing use cases, the model complexity has also increased. Here you can see the growth in the number of parameters here, or different number of models. For example, recently Google Scale Transformer has 1 trillion parameters that was released in January this year. And if this march continues by 2025, we may have models with parameters of the order of 100 trillion, which will actually match the complexity of the human brain, right? So as the use cases evolve, the model complexity keeps on increasing, and so does the energy consumption. Primarily because while the human brain is much more efficient in processing, today's hardware are still not there. Like the brain's computational efficiency is 100 times better than what today's hardware does. So there is clearly a need, right, to improve the hardware energy efficiency and also make the models themselves more efficient in terms of energy, the compute and memory that they use. And to continue this, there is a clear need to make the models efficient, and that is what we are going to focus on in our AIMET toolkit today. So on one hand, I mentioned that the Google Scale Transformer has 1 trillion parameters. A lot of the audience here in tinyML works on much more compact models. We heard in MagicWand talk from Pete, the model parameters also can be of the order of few hundreds to few thousands. So, but regardless, right, at both the end of the spectrum, these workloads impose very challenging requirements, and often these requirements are like conflicting and very constraining. So the workloads will require complex concurrencies or real-time low latency performance, and a lot of these applications have to be always on, right? So to meet these requirements becomes very challenging, especially on like mobile devices or edge devices like smartphones, wearables, low power IoT devices and such. The memory is a border issue in these devices. Similarly, power is a concern. Like we want the devices to last longer without having them charge off so often. So there is a to make the all edge AI all prevalent, to make it much more efficient, enable more and more use cases. We need to ensure that the power and thermal efficiency of the models we develop can be achieved properly on the device. And it is really paramount to continue to drive this path forward, basically. So to achieve this, right, it's not a simple problem. So what we do at Qualcomm is Qualcomm is a leader in low power SoCs and also AI accelerators. We have industry leading fixed point AI accelerators. To complement that, we have put significant energy into model efficiency research. And the model efficiency research, basically the goal is to eke out last bit of performance from the models and make them run more efficiently at the edge. The problem is challenging, needs to be tackled from multiple dimensions, right? And so we take a holistic approach. Our research spans like multiple facets, like we do focus on quantization, make floating point models into fixed point models, we get memory compute benefits, compress the existing models, like prune some of the channels, say, or remove the redundancy from the existing models. So quantization compression tackle the problem of making current models more efficient. Same time, we also have research on the network architecture search. So how can we find the better models from the get-go? And once the models are available, BFO models are optimized, then we also focus on compiler research. The idea here is basically to make the models run more efficiently, translate into how the models available in say PyTorch TensorFlow into hardware-friendly, efficient graphs for inference. So as you can see, it's our research spans a broad breadth. Today we are going to focus on quantization and compression. AIMET's current focus is on quantization and compression. But for folks who are interested, we are going to have a webinar on network architecture search in early April. So I encourage everyone to visit Qualcomm's website. You can sign up for that webinar as well. That will give you a broader overview on the other research activities that we have. So what our approach is to take the research we have and then bring it into commercialization either through products or through our tools like AI Model Efficiency Toolkit, which we have open source. So we are very excited in that sense, right? That it's not just research, we are enabling the broader community by offering these tools. Our research has shown outstanding results on both quantization and compression fronts. It has been highlighted in a lot of top tier conferences. For example, the data-free quantization that was presented in ICC 2019, it set the benchmark for like a state-of-the-art 8-bit inference using post-training techniques. It pushed the envelope further with add-around technique. It enables even 4-bit quantization with very good results. And then now, once you say 8-bit models can be quantized, if models can quantize to 4-bit, and the next frontier is like mixed precision. And how can we achieve the best of both the worlds, like 8-bit, 4-bit, or any other bit with precision, and get a good accuracy as well? And that's where like Bayesian bits, which was highlighted in Europe's 2020, it enables mixed precision models. Now, what we do, we take all this research that our innovators do at Qualcomm AI Research and bring it into our AI Model Efficiency Toolkit. We also have an AI AIMET model zoo. I'll briefly talk about it in a moment. So with these efforts, right, we are truly enabling the whole ecosystem to move towards fixed point inference. Fixed point inference has a lot of power benefits and memory benefits, and that is really the path forward as we see for enabling efficient edge AI. So what is AIMET, right? Like AIMET basically, in a nutshell, if I had to summarize it, goal is to make AI models small. It automates the model optimization process. So the user doesn't have to spend a significant amount of time and effort using AIMET. That task becomes much more easier. So let's say there is a trained model available. It can be TensorFlow or PyTorch model. The AIMET has library of compression quantization techniques. So you can embed the AIMET algorithm in the existing pipelines for TensorFlow and PyTorch and get optimized models. So again, the output would be again a PyTorch or a TensorFlow model as in the original format. And these models can then be deployed on target through the various runtimes basically. So in that sense, AIMET is hardware agnostic. It can enable broad swath of hardware and devices. One key aspect that I also touch on is like how we designed it in terms of the ease of use when I show the architecture. And we have, as I mentioned, we have open source it. It's available on the GitHub. The GitHub community is growing. We are actively bringing more and more features in. Today we have quantization compression features. I will just list them out next slide, focusing more on convolution networks. And then like you saw in the Pete's presentation, like there was a question on R&amp quantization, how to enable R&amp quantization, LSTM and such. We recently enabled that as well. So the point being, it's a very live and active project, and we are making continuous efforts and improvements to bring more and more features into the open source AIMET project. So here's a high-level overview of all the features today AIMET has and the benefit that it can provide. So we focus on quantization here. So we have state-of-the-art int8 and int4 performance-giving features. So we divide quantization features into roughly two buckets: post-training quantization techniques and then techniques that require model fine-tuning. And we have data-free quantization. It's already available. We will talk about some results as well on that. And then adaptive rounding, which will be coming soon. Quantization hour training can get you to a very good performance, close to FP30 even for very challenging workload. So we support different quantization options and also quantization simulation to get a sense of what will be the performance look like if you take it to a hardware. So that completes a quantization picture. In the compression front, we have techniques for efficient tensor decomposition. So like singular value decomposition techniques that remove the redundancy in the networks while maintaining good accuracy. Similarly, we have channel pruning technique, which removes the redundant channels in convolution layers. So the idea is you have a kernel with 32 channels. Some of the channels may not be adding much to the final model accuracy, then you can remove them. And to complement the quantization and compression algorithms are one thing. We also want to make sure that the user really gets insights into what's going on behind quantization and compression. So we have some visualization tools as well. The user can plot like weight histograms, ranges, also look at the sensitivity of different layers to compression, quantization, and such. And that may also help in like if they had to rejig their model, tweak it around here and there. Along with our quantization compression techniques, it can become very useful for them. Clearly, quantization has a lot of benefits. If you have a floating point model, 32-bit, and if you take it down to 8-bit, the memory directly reduces by 1/4. Compute clearly improves on the accelerators designed for 8-bit inference. For example, we have seen speedups of from 5x to 15x compared to just like running floating point versus on AI accelerators with 8-bit support. And all this is achieved, right? Like again, while maintaining model accuracy, I'll highlight some examples that again, a lot of questions were there in the previous session where, oh, how do you maintain model accuracy? What it takes for quantization? All these techniques enable that we have in AIMET. And the best part is they're all simple and easy to use. We have to put a lot of emphasis and focus on making it very easy to use for folks. To give a high-level view of the architecture here, right? So AIMET basically, as I said, underneath there is a library, optimization library, which has all the algorithms for quantization and compression. The library is, in a sense, agnostic to the framework, whether it be PyTorch or TensorFlow. Then we have simple extensions for PyTorch or TensorFlow, which enables the user to plug in the AIMET library into the existing pipeline. So you can see, right? It's not like someone will need to adopt a new tool per se. It very seamlessly, easily can fit into the existing workflow a user will have with PyTorch or TensorFlow. And the APIs themselves are very user friendly, and they are minimalist. If you wanted to do a compression, here's an example with a one or few API calls, like say compress underscore model. The model, you pass in the model the scheme that you want to try in here in the example special SPD and search, and then the AIMET will do the rest given this configuration or the API call. Similarly, if we have to do quantization, there are simple APIs available. Like equalize model is a part of the data free quantization techniques here, and we can invoke that and easily quantize the model. Abhijit will talk more about like a bit more details and even will give some examples, and we'll be glad to take more questions as well on the APIs and how to use them as well. So all this AIMET library is available on GitHub. I invite everyone to visit github.com/quick/AIMET. And what we have done is like along with the code available, we have detailed documentation describing each and every technique. We have even best practices documented there. Or if you have to do quantization of a network, how will you go about it? Like starting from weight quantization to activation quantization, which schemes to use and such. There are code examples available, and the best part is there are video tutorials which actually walk you through some toy examples for quantization and compression. And this can enable a user to get going in a very fast manner. And because of this, right, like because of this simplicity of use, what we have seen is AIMET has outgrown from just being an R&D project, and now it's being used on real-world applications by various partners that we have. Here I'm going to highlight one particular example, like an extremely popular and real-world application is Snapchat. Snapchat needs no introduction. Snapchat is used by millions of users every day. Like they are creating billions of snaps and having fun with the Snapchat app on their smartphones. For Snapchat, the device camera is essential, like to create the wonderful experience with the lenses. So what the lenses do are like they create a fun, engaging experience when you are interacting with your family and friends. The lenses essentially do a style transfer. They can transform a person's face or morph it into different avatars or lenses that you choose. And all this magic happens in real time. Right? So the lenses are essentially driven by AI. The inference of these neural networks, how fast it performs is critical to ensure the user sees a smooth video experience during live preview mode and such. The requirement is to have even more than 30 FPS frames per second for the video for a smooth and enriching experience. And AIMET helps make this happen possible in real time on the device by making the lenses run more efficiently. And what this translates to is like higher performance, reduced power consumption, and very satisfying user experience. And user engage more and more with this kind of capabilities, right? So this is truly wow. It shows the power of AIMET, how it enables real-time, low latency applications. And the list will only grow as we bring more and more features into AIMET. To complement what we have today in terms of the algorithms, recently we also released AIMET Model Efficiency, AIMET Model Zoo. So it is essentially a collection of pre-trained 8-bit quantized models. We have PyTorch and TensorFlow models across a lot of popular tasks like image classification, object detection, semantic segmentation, pose estimation, and we will continue to grow and bring in more and more use cases into it. So it's not just the model, right? So user can easily go to the, again, this is available on GitHub, that the AIMET Model Zoo GitHub web page or the project. Users can go and download this ready to use models. But more along with the models, right? Like what we have done is to empower users. We have also given example scripts how to use the quantization techniques by the users. So they can even take this script, example scripts, and apply it on their workloads, and then that enables to again to reduces their effort, and the developer can focus actually on developing more better applications, and then leaving the model optimization process to AIMET. So on this slide, I'm highlighting some of the performance that we see on the models we have put up. Quantization, when we talk about quantization, model accuracy question always comes up. Oh, what is the accuracy of the quantized model versus the floating point model? And here we are showing that across wide range of use cases, the model performance is very comparable. Like all the numbers in the circle here show the performance of the int8 model versus FP32 model. And we see the reduction in performance is very negligible. And this is achieved through the state-of-the-art techniques we have in AIMET. If you look at like some examples, say efficient net light model, which is quite popular for classification, we see less than 1% drop, 0.1% drop in accuracy compared to floating point FP32 model. So which is outstanding, right? Essentially, you are getting the the same accuracy with significant reduction in like the model size, and a speed up that you get is an additional bonus. Pose estimation, which is also very popular for some of the other applications like AR, VR, and stuff. And there also we see compared to the FP32 model, the loss in mean average precision is negligible. Even for super resolution like tasks, we have shown the good performance can be achieved. Similarly, on the PyTorch side, we have models where again classification with MobileNet V2. But I'll show an example on the segmentation on the next slide. Even for like speech models, like here we have a deep speech model for speech to text. Even that, the word error rate reduction is like compared to the FP32 model is 0.3%. And again, depending on the applications, the tolerance may be different, but then we have all techniques that achieve enable you to get best performance across the board, right? And with a new feature that will come in like add around, we can even push the envelope further through. So if someone wanted to go to 4-bit, then that can be enabled. We had a demo in NeurIPS 2020 where we showed that even with 4-bit weight models, we had a great performance on object detection tasks for autonomous driving or even semantic segmentation. So I would encourage if anyone is interested in like downloading quantized models optimized for like a int8 inference, please visit the AIMET Model Zoo GitHub web page, and you will be able to download it, the models, also get the scripts and examples to apply to your own models. So here I'm highlighting the difference in like picking one particular model from this previous slide. Like
Hey, Chirag. Yeah, Chirag, just one comment. Could you enable your pointer in PowerPoint so that we see more where you're pointing? Wonderful. Yeah, that's nice. Just one quick question. We have a lot of questions on the Q&A. So do you want to wait for the end of your presentation, or do you want to stop at some point? It's really up to you.
So actually, I'm going to end in this slide, and then I'll be glad to take the questions.
Perfect.
So perfect.
Okay. Wonderful.
Yeah, thank you. So this is an example of the DeepLab V3. DeepLab V3 Plus is very popular for semantic segmentation. Like the idea is to outline different objects. In this case, we are like segmenting people. And this is the FP32 original model performance. You can see the outline for both the persons is very accurate. And let's focus on the rightmost column here, where we just do traditionally baseline quantization the non-AIMET integer 8 performance, you can see, like, for example, this person, the lady here, the segmentation is completely off or missing. Yes, but if you use AIMET quantized models, which is available on the Model Zoo web page, the performance is essentially similar to FP32. But it's very hard to even spot differences, right? Uh, so this shows the power of the AIMET techniques we have in AIMET, and also how we are enabling the broader AI community through that open sourcing of the toolkit and the models that we have made available. So with that, I'm going to take a pause. Abhijit, my colleague, will walk you through more details, deep dive into the techniques themselves on quantization and compression. But let me take a pause, and I'll be glad to take questions. And Abhi, feel free to jump in as well. So for the Q&A.
Yeah, wonderful. Thank you. Thank you so much for the nice introduction. Oh my God, I'm looking forward to hearing about how to use it and the results now. So first question is, let me look at the, oh my God, there are a lot of questions here. Let me try to go down in the list. Yeah, so first question.
Edith, by the way, your camera is off.
Oh yeah, excuse me. Okay, here we go. Here you can see me now. Yeah. So one question here is from, let me go from the list. It's all out of order, but I think we can do all the questions here. So from Wenjilu, how is AIMET different from TF-MOT? Is R&amp supported?
So maybe if I get the first question right, the question was, how is it different from TF? Sorry, what was T?
Yeah, TF-MOT, TF-MOT.
So I'm not completely familiar with the TF mods, but if you're comparing with TensorFlow, quantization or compression techniques or PyTorch, where see the baseline functionality is similar. The idea is the same, how you quantize, but the techniques that are to achieve the performance, they are very different. Like what we have, the data-free quantization technique or the data-free quantization technique or the adaptive rounding technique, how we do quantization or fine tuning. There are significant differences, and that is what gives a good performance benefits for us.
And I think an additional question is R&amp supported?
So R&amp quantization support, we just recently added that. So I encourage you to check it out. We are still working on like enhancing the documentation, put the code examples and tutorial for that. But the basic support is there today now. So.
Okay. Another question is from Aya, I think. How does the AIMET compare to Intel's OpenVINO toolkit?
A very good question. Thanks for asking. And as I said, similar to other frameworks or other toolkits that I have, so we do believe like our techniques have gives the state of the art performance, and which is what we highlighted in our papers as well. So the difference really is like, sorry, is there a comment or question?
Yeah, no, I think we're
Okay.
yeah, I think we're good. Your voice
Okay.
was just breaking. Are you okay? Yeah.
Yeah, I'm fine. Yeah. So again, like it's similar to TensorFlow or PyTorch or OpenVINO, right? The difference is really in the underlying techniques, basically. And that's what you will see in more detail in the next section, where Abhijit will talk about how do we do data-free quantization, how do we do add-around, and that will maybe make it more clear, like how our algorithms are very different than what is out there. And so similarly for the compression and quantization.
I think you've been teasing everyone with the introduction. So yeah, one question that I think, and me included, we liked a lot the snapshot example. One question from Felix is that running on device?
So Snapchat application for the lenses, they are running on device. Yes. So, but I'm not sure if you are asking if this animation is on device. That is not the intent. Here we are showcasing the use case of the lenses. But when you on your phone, if you use Snapchat, then it will be running on your device, basically on Snapdragon.
Depends which kind of device we're talking about. Yeah, but it's running on your phone if you want to, right?
Exactly. Yes.
Yeah. We have another question from Enmus. Does the ML model need to be retrained after your compression or quantization flow? And if so, does the retraining needs to be fine-tuned again? So I think it's a question about retraining after compression and quantization.
Again, very good question. Thanks for asking. So on the quantization, we have two sets of techniques. With the post-training quantization techniques, you don't need to retrain. And a lot of the times what we have seen, like this technique give very good performance, where we have seen like less than 1% drop in accuracy with these techniques, even with post-training quantization. So if the end KPI, if you are satisfied with less than 1% drop in accuracy or similar in the same ballpark, then you don't need to fine tune. But if you are not satisfied, then you will have to do fine tuning using quantization over training. On the compression front, all these techniques actually require fine tuning. So as part of the compression process itself, AIMET will fine tune the model. So we will enable you to do fine tuning. So fine tuning is needed for the compression techniques.
Okay, makes sense. Yeah. I think we have time for one or two other questions, and then we will switch to the other speaker, and maybe we'll come back afterwards if we have more time. One question, I think you kind of replied in some ways, but does the AIMET use MOT and TensorFlow optimizations under the hood?
We don't use TensorFlow optimization. We do use TensorFlow sort of backend. If the original model was in TensorFlow, we'll make sure we take the TensorFlow model graph and then optimize it and then give out a TensorFlow model basically. Yeah.
Okay, thank you. Another question from Sandeep, which has been upvoted. Does the AIMET support custom quantization schemes like integer 4 for a few layers and integer 8 for some other layers?
Okay, the question is about mixed precision, essentially.
Yeah, exactly.
Today we don't have mixed precision feature directly, but still there is an ability if someone had to custom configure, like the framework is very flexible for when we do this quantization simulation. For each layer, you can evaluate the sensitivity if you put the layer into 8-bit or 4-bit. And then you can even configure for the whole model, or what is the bit precision I want to use it. So it is possible with some configuration, but today we don't have a automated algorithm that get me the mixed precision, and that is something that we are working on. And I will say again, T is saying look forward to the future. So.
Yeah, that makes sense. Yeah, thank you. There are a lot of questions around TensorFlow and how it is supported. So maybe one quick question: does the AIMET support? Does the AIMET support TensorFlow version 1.13?
So no, maybe Abhi, if you want to take that, go ahead.
Yeah, so we support TensorFlow version 1.15 today. That's what we have tested with, but 1.13, 1.15 should be kind of close to each other. So yeah, you can take the open source code and like recompile it with 1.13, and it should work, I think, for the most part.
Okay. One last question that I think is interesting, and maybe we can move forward, is you mentioned that AIMET is hardware independent, which is correct, I assume. Is it possible to use a compressed quantized model with TensorFlow Lite for microcontrollers? So that's a very specific question here.
Yeah, so these techniques that you see in AIMET, and I'll go into more details on it, they are optimization techniques. So I think once you have an optimized model, you can take that optimized model to any runtime for that matter.
Mm-hmm.
So yeah, as a short answer, yes, you can do that.
Okay, wonderful. So thanks a lot. So for KHOBARE is Director of Software Engineering at Qualcomm Technologies and currently leads the development and model compression and quantization software tools. So I think you're going to present then compression and quantization, which is great. And also part of the Qualcomm AI research program at Qualcomm Research. Prior to this role, Abhi worked on cellular research for various 4G and 5G technologies as part of Qualcomm Research, helping prototyping several pioneering features like LTE Enhance and LTE WLAN coexistence. He also contributed to Qualcomm's commercial cellular stack for 4G And prior to that, Abby worked at Intel, where he worked on high-speed TCP offload using network accelerator chips and server load balancing solutions. So Abby holds a master's degree in computer science from Virginia Tech. Thank you, Abby.
Thanks for the introduction, and yeah, happy to be here presenting to you guys. So, so I'm gonna take over from where Chirag left off, and we're gonna go a little bit more into detail. Okay, so we talked about quantization, and so why do we do quantization? So I think the main benefits you see are a sort of order of magnitude increase in performance per watt. So essentially, like if you think about inferences per second per watt, and this comes from like multiple reasons. So one reason is obviously compared to doing floating point compute, integer compute is more efficient. But also using lower precision integer also helps with both compute, so lower compute, lower size, but also helps with memory bandwidth, and so that also has an effect on performance. So there's a lot of nice holistic reasons to do this. And yeah, the actual numbers may differ from model to model, but you can get like a big order of magnitude improvement. And so the main thing is like, okay, you can get all these benefits, great, but what cost does it come at, right? And the cost is because of adding quantization. You're going from like very high precision numbers to very low precision numbers, like 8-bit numbers. You can think of them like they can only have one of 256 values. So you get there's a noise introduced into the model. And so the challenge is to do low precision integer models, and then also get back the accuracy similar to floating point 32. So that's, I think, where the challenge comes in. So here's a sort of toy model here with some layers. And so when we talk about quantization, what we are talking about is you have these layers. I think in this particular toy there are like a bunch of convolutional layers over here, and so each of these convolutional layers is running in some lower precision compute. But if you think about it, like when you run a particular layer in a lower precision compute, let's say 8 bits, and so the output of this layer would actually be at a higher precision, because you to do multiply accumulate, you need accumulator precision storage, and so you will output of this layer would be at a higher precision. So now you got to convert that higher precision output into a low precision input for the next layer. And so that's where, and this keeps going on and on, right? Every layer computes, does some output, and that gets decimated down to lower precision input for the next layer. And so this, as you keep doing these operations, every time you do this operation going from high precision tensor to low precision tensor, that's where you can get quantization noise. And the pic and the sort of animation on the right is it's an analogy. So we are probably aware of how pixels or bits per pixel for images. You have 24 bits per pixel, and you get a very nice color image. If you go down to like 1 bit per pixel, you get a black and white, very stark image. So this is just an analogy, and quantization is similar. I think if you, at a very analogy level, so you basically can, as you reduce the number of bit width, you are reducing your choices, and so you're introducing more noise. So here is a sort of a little more deeper dive into that. So if you look at, this is a model that's flowing in the reverse direction. Now it's flowing from bottom to up. So this is the start of this layer and end of this layer. And so if you look at a convolutional layer actually has, the convolutional operation, and then it has, maybe a bias add following the convolutional if there was bias, and so on and so forth. So what AIMET does, given such a graph, is it adds these simulation nodes into the model. So these green nodes are simulation nodes. And where you place the nodes is important. So it allows also to configure how the nodes get placed. Is a node placed for biases or not placed for biases, or it also depends on how your runtime runs it. But so based on what you know about your runtime, you can actually control where these nodes get placed. And what these nodes do is they essentially are simulating noise. So if you go from a 32-bit floating point weight to a 8-bit quantized weight, this node will sort of simulate the noise that has occurred for that. And in this example, we are showing 32 to 8 and 8 flowing into convolution, but this is a logical view of things. This would, take it back into a floating point number, but with the lower resolution. And so your convolutional operation would operate just like before. So if this was either a PyTorch graph or a TensorFlow graph, your actual operations remain the same, and then AIMET just adds these simulation ops. So what this means is, like, here on the right, we are showing a number line. So these are just x-axis is just numbers. And these blue dots here are showing some tensor values. So your tensor values on a actual floating point number line, there's lots of precision. You could say infinite precision with 32-bit floating point numbers, let's say. And so your dots can be all over the place. But when you talk about quantized runtimes, and let's say you're talking 8-bit quantized representation of this tensor, then you only have a few discrete choices that you can place. So you have essentially 255 or 256 numbers to play with. One number, let's say you want to represent your 0, and so you have 255 other numbers to play with. And you can put it on this number line in a uniform fashion. And so what happens is you have this less resolution over here. So if you take the floating point numbers, and if they fall beyond your range, then they get clamped to that range. If they are within the range, then they are within the range, but they get sort of rounded to the nearest grid point. So this is where all this red arrows are showing essentially where the noise is coming from. So the question is, how do we choose this range? And so AIMET has different techniques to choose. Like you will see in TensorFlow Lite, for example, there is a technique just for observing values. Like if you look at this green dot, you can observe all the values going for some sample images through the model. And then at the end of that observation, you get like a range of numbers that it has seen. And then you can use a absolute min max of that range and like pick your absolute min max. So that's a scheme allowed in AIMET as well. But you can do a little better than that. You can also, there are histogram based schemes where you put these numbers, you decide these numbers based on essentially the, throwing out some outliers which are less important or seen rarely. So you throw out outlier values that are rarely seen, and you increase the range. So if you clamp it, you get noise here for these outliers. But the outliers, if they are very rare, then the noise, cumulative noise, is very little. Whereas you get much more resolution over this range here, and so you reduce the noise for these values within the range. So when we, in AIMET, we follow this kind of naming convention, and it's just made up. But essentially, we have what we call level 2 techniques and level 3 techniques. And so what level 2 techniques we also refer to as post-training techniques. So meaning these techniques don't require any fine tuning. after the technique is applied. You may require some data, like generally unlabeled data. So you can, and again, not a whole lot of data, let's say on the order of hundreds of samples. And then level 3 techniques are techniques which require like fine tuning. So there are obviously, if you go down, like level 3 techniques are more robust, but they require more effort. Whereas level 2 techniques, since they don't require fine tuning, require less effort. But for some cases that may suffice, and other cases, if they don't suffice, then you can go from level 2 to level 3. So
Hey, Abby,
yeah,
we have quite a lot of questions. Do you want
yeah,
to just
yeah.
let me know when you think you want to pause on quantization, and then I can ask some questions.
Yeah, let's do a few questions now, like maybe
Okay.
3, 4. Yeah.
Okay. So one of the most body questions. So the first one is from Felix Marty. So how do you explain the differences in accuracies between models coming from either PyTorch or TensorFlow? So Felix would have expected the same.
Yeah. So yeah, I don't know exactly the intent behind the questions, but if you take a model, I mean, my interpretation is what you're asking is, if you take a model, let's say MobileNet V2, and then you have a TensorFlow version of the model and a PyTorch version of the model, and maybe from a quantization perspective, why is there a difference sometimes observed between these models? And I think in my experience, I think the differences come because of how the models end up being trained. So as you train your models, they settle at different points, and when you try to run these on quantized targets, like the previous picture showed, there's different like noise that can be introduced just from the perspective where the model, the final trained model settled. And so I think that's where these differences may come from. But like applying these techniques that AIMET has, like including, we'll look at cross-layer equalization and add around and so on. It tries to sort of minimize these differences and then get back the accuracy. Also, you can also apply quantization-aware training on top of that.
Okay. Yeah, there's one question coming back a lot around TensorFlow Lite. So have you done some benchmark against TensorFlow Lite quantization tool?
Yeah, we believe there are some, we have done some sort of numbers, but yeah, our intent here is not to, necessarily, sort of compete between tools. I think this is a collection of, if you think about this whole thing, it's a collection of tools. And like you can apply certain optimizations from AIMET, and you can take that model, that TensorFlow model into TensorFlow Lite, and apply further optimizations, and then runtime optimizations and so on. And so I think these tools can actually coexist with each other. They don't need to
because they are all available. Yeah, people can still use the tools for their best fit in their context. So that's good to have a large number of tools to use. Yeah.
Yeah, it's like a toolbox.
Yeah, exactly. Yeah. Yeah, so one other question is from Sri. How does AIMET mesh with TVM as a backend?
Okay, that's a good question. So TVM, is a sort of compiler framework, and we've done some experiments with taking AIMET optimized models and into TVM. I don't have any sort of results to show you, but yeah, in general, I think this actually works very well. AIMET does model optimizations and produces, if you take a PyTorch model, you end up back with a PyTorch model. Which you can like export to Onyx, take it to TVM, and then TVM can do runtime optimizations, which is what it does as part of its sort of compilation, and it can optimize the model's runtime. So they can actually coexist with each other.
Okay, is that something that you have experienced yourself?
We have done some sort of internal experiments with that. Yeah, I think it worked out well, I believe, from
Okay, so maybe
not
I
a
would
whole lot.
encourage, so maybe I would encourage the attendees to reach out to you if they want to have some specific guidelines for doing this.
Yeah, absolutely.
One other question, are the accuracies shown for quantization aware training or post-training? So are the accuracy, yeah.
hold on to that sort of thought, and I think we'll look at some techniques, and then we can see the sort of accuracies that they bring.
Okay. So then one last question, and I think you can move forward, is can you expand on the motivation for using quantized and pruned models instead of designing floating point models with much fewer parameters? That's a usual question.
Great question. And yeah, I think there is probably, not one answer to anything. I think you can try different ideas. But one thing, in my sort of experiences, if you start with a very small model, like a very optimized model, it's kind of harder to train such a model for your task. So having a little bit of over parameterization is actually helpful, in the case of, training it for the tasks that you're, interested in. And then, then in addition to that, now when you want to take it to target, you want to optimize it for like inference. And so when you go from a sort of optimized for training larger model to optimized for inference, then now you can utilize these techniques like quantization or compression. So you kind of, little extra steps, but you get it sort of best of both worlds.
Yeah, exactly. Thank you. I think we can move forward. So please continue asking questions on the event. The upvoting is working very well here. So thanks a lot. Look at the questions asked by others. If you want to upvote instead of asking a question, you're very welcome. We will have some time at the end of the presentation as well to reply to all of those questions. These are all very good questions, so please continue. It's also making my job easier, so thank you.
Okay, so I'll skip this slide to go into the slide on data-free quantization. Oops. So data-free quantization is a technique that helps for certain models. It's I think provides marginal benefits for other models, but for specific models, it applies a lot of benefits. And so some of the models that we have seen a lot of benefits with are like the MobileNet kind of architectures, version 2, for example, or version 1. And then also like other models that use these kinds of architectures and its backbones, for example. So this it's a term coming from the paper from my colleagues in Qualcomm AI research, but it kind of takes into two techniques into account. So one is called cross-layer equalization. We'll look at it in the next slide. This involves like rescaling weights between neighboring layers. And the second thing is called bias correction. So this is observing, sort of shifts in values at layer outputs and sort of accounting for those shifts by changing the bias parameters. But in general, for these, so data-free quantization is one of those level 2 techniques we had looked at before, or also what we would call post-training techniques. So it doesn't require any training afterwards. And so the flow looks actually pretty attractive from a user perspective, because you start with a PyTorch or a TensorFlow model. And then once you apply these techniques for bias correction, you may require some unlabeled data samples. If you had batch norm layers, it doesn't even require the unlabeled data samples if the batch norm parameters were or layers were in the right place. So that's the reason for calling it data free. And then you go from apply these optimizations and get back a PyTorch or TensorFlow model. So a model parameters have been changed, have been optimized, but the model is still a sort of full first party PyTorch or TensorFlow model. And then you can take this to your favorite runtime like TF-Lite or the Snapdragon, neural processing SDK from Qualcomm or whatever other runtimes you have. And this path doesn't change. Going on. So here's what this cross-layer equalization is doing. And this is a simple technique, but it's kind of very effective in practice. Most ideas are, good ideas are simple. So what this is doing is I would look at the bottom left over here. So this is a picture of a particular layer in I think in MobileNet v2, and I don't have the layer quoted here. So it's one of the sort of popular pre-trained models that you can see. And what this is showing on the x-axis is just channels. So the data or weight tensors for that particular layer have been sliced by from an output channel perspective. And on the y-axis is range. So this is just showing, what's the range of values that that tensor values take when sliced in that channel dimension. And so the interesting thing you will see, and as using this kind of box plot strategy here, but you will see if you see some channels have a humongous range, like they go from 100 plus 100 to minus 150, and a whole bunch of channels are have very, very small range, which is just around 0, like let's say +1, -1, or something on that order. And if you see, if you do a per tensor quantization technique for this weight, then you have to pick your poison. If you take this range into account, then you're going to destroy these other layers because all of those numbers would map to 0 or close to 0. Whereas if you take this only these sort of channels into account while picking your min max, then for these other channels you're going to destroy them because all of their values will get clamped to one value. So you have you have to pick your poisons over here. But I think what you can do going under top here is you can recognize that there is this wide variation in ranges across channels, and you could scale them down. So you could scale some of these big channels down and scale these small channels up. And you could reverse scale the input channels of the next layer. Right? So this is again the next layer's sort of weight tensor. And if you scale this down and scale this up, mathematically exactly the same. So no, from a floating point perspective, this is an exact operation. But from a quantization perspective, it's a big win because now you have a much reduced range across all the channels. And this is much easier to represent in quantized values. And you have much less quantization noise. So you get much better accuracies. So going on, and then you can apply these techniques sort of in sequence. So you can, apply the cross-layer equalization and then apply the bias correction and so on and so forth. And in practice, what we have seen is actually you can get pretty good numbers. So these numbers are showing only with the data-free quantization techniques listed over here. I kind of only discussed this in detail, but I think you could read the paper for explanation of the other techniques as well. And so here in this case, we have MobileNet v2 top 1 and ResNet 50 top 1 and DeepLab v3. So 3 models. And if you see the difference from after applying DFQ, you actually get kind of very close to the original floating point accuracy. So all of this is with 8-bit quantization across the board. Some models like ResNet 50, they are actually very easy to quantize, and so that's good. But MobileNet v2, if you didn't apply these techniques and if you just looked at analysis in this particular model based on that big range that you saw, it has a dramatic effect on reduced accuracy, like it goes almost close to zero actually. But with these techniques, you can dramatically bring back the accuracy to within 1% of where you left off. And what we have seen also in practice is like you don't have to stop here. So once you have this starting point, then you can apply quantization aware training on top of it, which is also what AIMET will help with. So here's a sort of another post-training technique, another level 2 technique called add-around. And we presented this at ICML last year. Again, other research coming from my colleagues in Qualcomm AI Research. And this is a very interesting technique again, also a very simple technique. But so what the observation here is, what generally happens, we looked at these, high precision floating point numbers, and then we looked at the quantized representations of those numbers. And if you're talking, let's say 8-bit quantization, you have, essentially 255, or 256 numbers to map all of these floating point numbers to. And so what you end up doing is you end up rounding. So if you had a number over here, and these are like grid points, obviously it's not showing 255 grid points here. But if you saw these quantized numbers, then you're going to round it. And generally what we do is we use nearest rounding. And this makes intuitive sense. Why take this guy to the sort of other end of the spectrum? Why not take it to the closest grid point, right? That seems intuitive. However, this actually is not the best for quantized accuracy. So what would be better is if we could learn how to round. If we could learn, is this better choice or is that the better choice? And we can learn this using not a whole lot of data. This doesn't involve fine tuning. But what we can do is we can take a model, a reference model in floating point, let's say another model in quantized, and we can look at sort of outputs of both the reference model and the quantized model. And we can look at do a loss function similar to this. You can read the paper for more details. If we took a rounding vector into account, which is shown by V over here, and you sort of do a localized training for that particular layer using unlabeled data, because your labels are coming from the actual reference outputs from a floating point model. And so if you train this for a little bit, it actually, and this can be done almost in an automatic fashion, one single call to add around, and it sort of goes layer by layer and does these optimizations. You can see dramatic improvement. So for example, in this particular picture, we are showing semantic segmentation model using DeepLab v3. The floating point accuracy is at this point. Here we are doing nearest rounding, and we are using 8 bits for all layers, but the weight tensors are in 4-bit 4-bit weights. And so obviously, if you did 8-bit activations, 8-bit weights, you get decent accuracy. If you push it down to 4 bits, you see a dramatic drop. But with add-around, you get a dramatic improvement back in accuracy, very close to this floating point. And this is again with 4-bit weight. So this is, something sort of, pushing the boundaries of what we can do going forward. And here is sort of another model using also where we applied add-around. So this is an object detection model for a like a autonomous driving kind of use case. This picture shows like a San Diego freeway, I believe, where some testing was being done. And in this particular model, it's an object detection model, and it's essentially trying to find, where these vehicles are, and also classify the vehicle. So if it finds a car, and then it wants to know, draw a bounding box around it, and also classify it, whether it's a car or a motorcycle. And then presumably the ADAS algorithms can take different path planning decisions based on what kind of vehicle that is. So if you see in this particular model, again doing 8-bit inferences, you see dramatic drop in accuracy. Very challenging model in this particular case. And when we applied Adderall to it, we actually recovered back accuracy to within 8% of the floating point. And you can see it visually actually here. So if you see the bounding boxes are much more tighter around the actual vehicle. A lot of things that were not classified, like this car over here is classified correctly. Also, a lot of things were misclassified. And so this detection didn't happen for this car, but even some cars over there were misclassified here and classified correctly over here. So yeah, this is this is like an example that we had from late last year. So underlying all of this is also a feature we call quantization simulation. So quantization simulation is the feature where we add these simulation ops into the model graph itself. And like I mentioned before, users can actually choose certain rules or specify rules on where these things get added. So some things you would notice in runtimes is generally you have an activation function like ReLU following, let's say, a convolutional operation, and like maybe there's a bias add in the middle. And from a quantization perspective, these three ops are sometimes in certain runtimes fused together. So what that means is you do the convolutional operation, let's say with 8-bit input and 8-bit weights, and then you keep the high precision tensor at the output, do the bias add at high precision, do the ReLU at high precision, and then you decimate it down for the next layer. And the reason to do that is, if you can imagine, like doing a ReLU operation on a high precision tensor is not a killer. It's a very simple operation to do, and so we can do all of this while the data is in cache. So like I think Pete was talking in the previous thing, there's like tiling that happens generally. And so once you get some data into cache, you can do all three operations together and then write it back to cache. So what AIMET allows you to do is to sort of place these ops at the right places based on your runtime. And then once you have done this, it is still, if you started with a PyTorch model, it's still a PyTorch model. It has some custom ops in PyTorch, or if you started with a TensorFlow model, you still have a TensorFlow model and with custom ops in TensorFlow. And you can now take this model through your evaluation pipeline and get an evaluation accuracy. So if you did this original model with the same pipeline, you get floating point accuracy. You take, with the simulated model through the same pipeline, you get your simulation of on-target accuracy. Now, if you replace this eval pipeline with a training pipeline, you get quantization aware training, because now in the forward pass, you are simulating the noise, and then in the backward pass, you can like sort of let the weights settle to handle this noise in the forward pass. So this slide is showing, how accurate can the simulation be, right? Because you are simulating and it's not really on device, and the device here is a phone, I think, running the Snapdragon Neural Processing SDK, and the column number 2 here is the simulated accuracy using AIMET simulation. And you can see for these models like ResNet 50, MobileNet V2, gets fairly close. I mean, so why do we want this to be close? And the reason to be close is so that you can be off target and get a quick understanding of what your on target accuracies are. So like if you're doing lots of different experiments, for example, somebody asked about mixed precision before, and you can actually go to these green simulation ops and change them. So you can put one of them in 4 bits, one of them in 8 bits, and you can or you can do 16 bits and 16 bits, or you can do different combinations, and you can get a very quick understanding of what did that do to your model accuracy. So yeah, in the future, we'll have more automated techniques of doing this mixed precision analysis, but you can do that like today. And then, of course, if you simulate this well, then your quantization aware training also gets you the best accuracy, because you're sort of simulating real like noise that you see on target. Is there any maybe questions we should stop for at this point, Adit? Or should I keep going?
Yeah, so unfortunately, I think my browser is just not showing the questions anymore. I'm just solving the issue in parallel, and I'll come back with the questions, okay?
Oh yeah, no worries. So I have just a few more slides to do, and then we can like open it up for questions. So Chirag mentioned, I think one of the things our aim with this toolkit is, you have research techniques, but we want to make these research techniques be available to actual users, like like yourselves, like maybe users who are very familiar with other domain tasks and how to train the models and so on, but not they don't want to be involved in the nitty-gritties of how do I do quantization aware training, or how do I apply DFQ. So we want to make these tools be very user friendly, and so we have put some effort into like creating very simple APIs for the users to invoke. Like for example here, a single call which basically applies the cross-layer equalization technique that I showed before, and it does it in place. You give it a model, and it basically equalizes that model in place, and done. In this case, this is a PyTorch example. So this is a torch vision model. Same thing, like we can create this simulation model that we talked about. And again, simple call to sort of insert the simulation nodes, another call to, use these observers to find, appropriate sort of min-max values for on a per layer basis, and then done, you're ready. So the simulation model, which is sim.model, is has the simulation nodes in, has the min-max or scale offset parameters already set, and now you can just send it to your own sort of evaluation pipeline, your user pipeline.
Yeah, Abby, what about going through some questions? I got the moderator role back there. Okay.
Let's do that.
So I think the first question you answered at the very beginning, but I think that's important to mention. Is the neural architecture search also part of this toolkit? I think you mentioned it at the beginning, but that may be worth saying it again.
You're right. So not at the moment. And there is research going on in our group to see how does neural architecture search play with both from a compression sort of use case, how get a more efficient model for target, so on and so forth. But yeah, not at the moment. It's not a technique part of AIMET at the moment.
Okay. So another question is, how will ADA round work together with quantization aware training?
Yeah, an excellent question. So it actually works pretty well. So you can successively apply them. Now it may be that again, these are sort of tools, and one may argue that if you're going to do quantization aware training, and which is a more generalized technique, then do you really need to do add around or cross-layer equalization and other techniques before? And in some cases, yeah, maybe quantization aware training by itself is sufficient. But in other cases, what we have noticed is like applying the cross-layer equalization or add around first, and then doing quantization aware training second. The first, applying these techniques, post-training techniques first, sort of takes the model to a good state. So it initializes the model and makes it easier to do quantization aware training. So you can sort of converge quicker and so on. Also makes the training like more stable. So that's our observations.
Okay. Another question from Sandeep Kumar. Is there some Windows support for AIMET?
So if you go to the AIMET repo on GitHub, so we have packages available for Ubuntu today. So these are sort of pre-built for you. But the source is there with CMake and so on. I think we haven't actually tested, building this on Windows, but I don't believe why it should not be possible. So it's not something that we have support for, if you may, but it may require tweaking CMake and involve like linking in the right libraries and so on and so forth. So I'm pretty
But
sure.
people can find some information in the repo, right?
Yeah, you can find information for how we got it to sort of compile for Ubuntu Linux, and yeah,
Okay.
you can sort of translate that into Windows builds.
Okay, so maybe another question before we move forward. Any plan to improve the current documentation with examples? So Ahmed is asking that the current compression API likes some details regarding the use of the eval callback, for example.
Okay, excellent question. Yeah, I think we have some examples today, but yeah, we can always do better examples. So I think we are working on that as we speak. I think there's a bunch of tickets you could see on the repo. Feel free to help us and contribute to that. I think few folks are already have
Yeah, definitely.
chosen to contribute to that. But yeah, we plan to add more examples as we move forward. Yeah, including with something like notebooks, which are more easy for people to.
Yeah. So it's a strong collaborative work. So yeah, if you're attending today, feel free to help and contribute. Okay, I think we can move forward. So it's 11:18. If we may spend some time at the end for a short Q&A, how long do you think you're gonna have right now?
I'll try to wrap up in like
Okay.
maybe 5 to 7 minutes.
Perfect.
So we talked about quantization quite a bit. So the other angle of it is, model compression, or you may refer to as pruning. So there are two techniques built into AIMET. So one is spatial SVD, which is like a singular value decomposition technique. So this involves taking, let's say, a convolutional layer weight tensor into two convolutional layers, and it says spatial because the spatial dimension or of the kernel itself will also get split. And so the reason to split it is so that you increase the number of layers, which is a reverse of what compression would mean. But the combination of these two layers from a compute perspective can be smaller than the compute of this layer to begin with. So that's so you essentially, by decomposing it into smaller layers, you achieve compression. And on the right is channel pruning, which is you look at input channels to layers and you simply delete some of the channels. And of course, which channels to pick is the key thing here. So we'll look in the next page with some details. But the interesting thing is, like, even though these techniques, we have found that they are separate techniques, but we could apply them successively. So you can combine them to actually get more gains. And here's a flow of how this works. So what AIMET does is it sort of provides, like, I think as you saw, intent is to make APIs be very user friendly. So with compression, you have this sort of choice to make how much to compress each layer, right? Let's say you wanted to say, I want to compress the model by half of its current sort of compute, let's say. But then how much do we uniformly compress each layer by half? And that's not always a good thing to do. So there is a built-in technique here, or a couple of techniques now, to sort of decide how much to compress each layer. So this is done automatically, and then the pruning is applied on top of it. And we can choose also what do we want to optimize? Do we want to optimize the size, or do we want to optimize the compute? So you can sort of make that pick that choice as well. And then like Chirag mentioned, these techniques, spatial SVD channel pruning, this generally involves, fine tuning after this is done. So the model right after compression would look like a compressed model is similar in format to the original model, but the accuracy of this compressed model will be, it'll drop depending on how much compression you do, can look dramatic. But then if you do fine tuning on top of it using your own pipeline, then you can gain back the accuracy. So here is the second part of this, how much to compress each layer, right? So there is this built-in technique called greedy compression ratio selection. And what this does is it does a sort of a layer by layer, per layer analysis of how much sensitive is each layer to varying degrees of compression. And so if you sort of visualize this through a graph, you can see that some layers, in the x-axis is sort of how much compression and y-axis is accuracy. And some layers can show like, can be pretty resistant to compression. You can compress them and the accuracy drop will be sort of gradual. Whereas other layers may show like this knee where there is a sharp drop in accuracy beyond a certain point. So what this technique does is it sort of analyzes this and then distributes the compression across different layers appropriately based on sensitivity. Yeah, and Chirag mentioned before, so we have added some visualizations in. Obviously, we could add more visualizations in, but here is a visualization to note that problem we were looking at, this cross-layer equalization, that in that technique we looked at where the ranges across different channels were very large, right? So there is a built-in visualization you can do even before applying any optimization, where you can see like plot on every layer of the model, for example. You can plot channel versus sort of amplitude or range, and then you can see like how much variations there are to begin with. So this is also showing a before and after picture. So in this particular layer, like the before had all these like spikes, and now after, you see like after equalization, the tensor values are so much in a tighter band, for across all the channels. So there are all these sort of visualizations that help you figure out, what was it to begin with, what did the optimization do, and so on and so forth. Yeah, to summarize, there are we have added these techniques for both for quantization and compression. We believe, on the quantization and compression side, these are state-of-the-art techniques. We get very good results for wide different range of models. I think Chirag talked about the AIMET model zoo. So the AIMET model zoo has all these techniques applied from AIMET onto those models and being available for you to just use. And we support both TensorFlow and PyTorch at the moment. There are user-friendly APIs. If you wanted to apply on some other model other than TensorFlow and PyTorch, you can use the existing code as sort of the optimization part itself is separate from the framework. So you can use the existing code as an example and add to AIMET other abilities. I think we would love for you to come and contribute and add more features, add more support, and so on and so forth. Yeah, and our feature set continues to grow to handle different use cases in the future. So that's what I had.
Yeah, thank you so much. Yeah, I'm the one uploading here. Yeah, that's good to hear so many details in that time frame. I think that's really appreciated by the audience here. We still have some questions. Before everyone is going to leave that session, I want to remind you to please rate and provide feedback to the session. You know how important it is for our speakers and for the conference. We always want to improve. And at noon, I want to remind you that they're going to be the award finalist presentation. So please join at noon. I hope it's not too late for you all from Asia. I'm sorry about that. I hope you're still woke up here. Some questions for you two, probably not always around compression, but maybe also some questions around quantization. Quickzang is asking, could the quantized model be deployed on neural accelerator like Hexagon?
Oh yeah, absolutely. So like we already talked about, yeah, you can take these sort of optimized models from AIMET and like run it on different runtimes, including the Hexagon accelerator from Qualcomm.
Yeah, that was good to clarify again. Thank you. Is there any tool available in AIMET for soft pruning or of filters while training the model?
So not exactly, I mean, that's a interesting sort of other possibility, and yeah, feel free to, connect with us via GitHub issues to discuss more. But yeah, at the moment, I think we have these compression techniques which are applied on pre-trained models, and then you can do fine tuning, afterwards. Chirag, feel free to jump in wherever applicable.
I think that makes sense. So we'll be glad to connect offline and discuss further.
Yeah, wonderful. Thank you so much. Really appreciate. So Enmus is asking a question. If a model has supported and non-supported layers for a quantization tool, will the model be quantized or is it need to be fully supported?
So that's a good question. So the answer is the following. So I think the way you saw how the simulation ops get added, and I think you can sort of control where the simulation ops get added. So yeah, the short answer is you don't need to be like, you don't need the model to be fully supported. So like an example would be, for example, we have recently added support for LSTM and R&amp and GRU layers. But let's say somebody had transformer layers in their model, and this is not something that we have currently added support for. So, they will, that's an unsupported layer. But I think the rest of the model would get quantized. And so your simulation may be off because, not all layers got quantized the same way. But then you can apply optimizations to the other parts of the model. And then when you take it to target to like like the Snapdragon SDK or TensorFlow Lite, then obviously if, depending on if the, all layers are quantized, then they can determine, parameters for the remaining layers themselves.
Oh, yeah. So Hun Choi is asking a question. Many of the techniques proposed for post-training quantization can be automatically considered in quantization-aware training by gradient optimizer itself. So the question is, any reason to do post-quantization if you have quantization-aware training?
Chirag, go ahead. Maybe good question for you to answer.
I think a very good question, Hunju. See, in my mind, post-training quantizations have different benefits. For example, post-training techniques are faster. And if through post-training, if the accuracy requirement is met, then you don't have to go over the overhead of the fine-tuning. We don't need to, still, quantization-aware training doesn't require as many epochs as you do for the model training. But it's still like even for 10, 20 epochs, you need to fine-tune the model, right? So versus post-training is much faster. So this is one. But even otherwise, right, even for quantization-aware training, we have found that having a good initialization with a good post-training technique, it goes a long way in making the fine-tuning process go faster, get to a better convergence. So we, in our mind, we clearly see value of post-training quantization, and it definitely complements the quantization-aware training kind of techniques.
Okay, thank you. So I think we have time for a very last question from Felix Marty, who has asked a lot of questions, so that's good that we reply to one. What explanations do you see to the very slight difference you may have between quantization simulation and on-device quantizations? Is that overflows?
So excellent question, Felix, and glad you're worried about the 0.1% difference there. So actually, we have some sort of done these experiments to see is overflows affecting us? And I think the answer is actually no. So the reason in this slight difference is because the simulation is still like simulating noise for where there are 32 to 8 kind of transitions, but the operations themselves run in in PyTorch operations or TensorFlow operators. So the operations themselves are running sort of floating point math, whereas on target you're doing sort of integer inferences, and the way you may do certain layers like sigmoids, for example, it may not be like the smooth curve that you see. There may be some piecewise linear operations that happen, and so on and so forth. So since it's not a bit exact representation of what the target does, it is a simulation. So there is a sort of slight difference between how layers are actually running off target and on target. And while those differences would be very, very minor, but across the model, then they kind of add up, right? So it ends up being in this sort of 0.1% difference from an accuracy perspective at the end.
Okay, thank you. I think we're run. Oh yeah, did you want to clarify something? Are you okay? Yeah.
No, yeah.
Okay, yeah, I think we're running out of time here. Thanks a lot. Extremely interesting. It was more than a tutorial. I think I've learned a lot, really. Thanks for providing all the details. Thank you so much. Thanks, everyone. Thank you.
I'd like to acknowledge our sponsors. First, it's ARM that develops software and hardware for tinyML. Qualcomm, Samsung. These three are the executive sponsors. And then followed by platinum sponsors. ETA Compute, Lattice Semiconductors, and the gold sponsors are BrainChip Corporation, Cisco, DSP Group, H-Impulse, Emza Visual Sense, General Matter Labs, Green Waves Technologies, Hymex, Imagimob, Latent AI, Maxim Integrated, Kixo, Reality AI, SenseML, Silicon Labs, Sentient, and Google TensorFlow. XMOS, and the silver sponsors are H-Cortex, HOTS, and SynSense. Again, we are very grateful for their continued support, and this is a great testimony that the foundation and this community is really of huge interest for the companies and for the whole world.